Looks like we are live. So, wanted to talk about a couple of things, start talking about a couple of things today. One of them was, let's actually go to Canvas and, oops, that's not the button I meant to hit. Go to Canvas and look at, let's just briefly revisit the subtractor program that we wrote last time, or Turing machine rather. And I thought I would actually show you guys maybe or we could think through sort of an alternate way to do it. All right, so here was our simulator. And then let's see, what state did we start in? We started in the start state, and let's give it a number. Let's just do 8 ones. Okay, and reset. And we got, oops, I forgot to put the star there for the initial position of the head. And there we go. Okay, so does this look familiar from last time? Yeah. So I think one of the things that seemed to bother both you guys and the other class was the fact that this didn't perfectly match the way that you do borrowing when you were in grade school, right? So when you did borrowing in grade school, you moved to the left, you crossed something out, and then you moved back to the right, okay? This is equivalent, but I thought, okay, fine. Let's maybe change it to be sort of grade school style. We'll end up with the same result. I mean, we ought to, right? But maybe it'll look a little bit different. Okay, so the subtract cases, let's see. We've got the return case will stay the same. The return cases will stay the same. We don't need to mess with those at all. Okay. But what about the subtract and the borrow cases? Well, let's maybe keep this one. If you have a 1 and you're subtracting from it, you just get a 0. There's no borrowing to be done, okay? So I think grade school style, the way that you guys would have liked to have done this was to say, okay, I'm going to start borrowing and I'm going to keep moving to the left until I hit a number that allows me to borrow from it, okay? Which in our case, what can you borrow from? Just a 1, right? Because we're doing this in binary. And you can't borrow from a 0. So if you hit a 0 that you can't borrow from, then you need to kind of go further to the left, okay? Now, what this will mean then is in order to change this to be more like grade school, right? So in fact, let me maybe kind of write this, is we'll have to actually add a symbol, okay? Because how do we know, for example, where the 0 was that we wanted to start borrowing from, or start subtracting from, where that sort of initiated the borrow, if you will? Well, if its symbol is a 0 and we've got other zeros, how do we know which one's which? We don't. Okay, we as humans might, but the Turing machine doesn't. Okay, so let me go to the sketch pad. Oops, wrong button. Where was I? There we go. iPad, auto. Okay, so let's switch to this. So grade school style, what was the number? Well, let's just pick, this for sake of demonstration, okay? And this is the binary number, not 1,000, okay? Okay, so if you were to do this grade school style, right, you would say, oh, I can't take 1 from 0, so I'll move over 1 spot. Oh, I can't take 1 from 0, so I'll move over 1 spot. Oh, I can't take 1 from 0, so move over 1 spot. I'll change this 1 into a 0, And then what do? I change this 0 to a 1, this 0 to a 1, and this 0 to a 1. Right? Yes. Okay. Um, and then I do the subtraction. So what's 1, 0? That's really 2, right? Minus 1 is 1. And then the other ones are just 1s, and we're done. Okay. Is that okay? Yeah. Um, okay. So look what we did. Let me mark this um, the last 0, okay, which it was the last 0 here, but in our case, it was the 0 that initiated the borrowing, okay, was one where we had to do something a little bit different, okay. A 0 turned into, well, okay, actually, we didn't have to do anything different because what ended up happening to the bit? What happened to the zeros? Like they turned into ones, right? So even if we think of the one that I've sort of boxed in green as somehow being different, um, are they really different? No. Okay. And so, yeah, I'm maybe not doing a very good job of explaining this, but um, the upshot of it is that right, that's actually exactly how we did this. When you borrowed, what did zeros turn into? Ones, okay? And how did you know that you stopped borrowing? You kept moving to the left until such time as you hit a one, okay? So this machine, um, the way that we structured it last time, right, does exactly that. Okay, does it perfectly match the way you might write it in grade school? No, and that's okay, right? Now, if we wanted to make this perfectly match grade school, like I said, we'd have to either introduce an extra symbol or something along those lines, and that's okay, right? Um, but and that extra symbol that we introduce could be, well, basically whatever we choose. But we would have to do this in such a way that at the end, what would be the state of the machine? Would there be anything other than ones, zeros, and the two X's at either end for this machine? No, that's how it should stop. So if you introduce sort of like a think of extra symbols as for our purposes here as being like temporary, you better undo them or tidy them up at the end. Okay. And that buzzing noise, by the way, I don't know. It's something in the floor, like the electrical outlet. Is it really annoying? Yes. Can I do anything about it? Sorry, I can't. Okay. Um, okay. So great. So we have our machine here. Okay. So the next thing that we want to kind of talk is about is so I'm going to introduce sort of a new language that's meant to be sort of slightly more abstracted than this Turing machine stuff, right? Turing machine language, if you will, is sort of the most minimal language that we could possibly have in some sense. Um, and can we do essentially any computable thing with a Turing machine? Yes. Okay. Um, that in some sense that's the definition of computability, right, is that you can do it with a Turing machine. So let me load an example program here just to show you that how this can get really nasty. Okay, so this is a program that the person who built this simulator wrote to add two binary numbers that are separated with a space. Okay, he's used spaces as a separator. We could have used x's as a separator, whatever, right? Got to have something to keep track of which number is which. And so what I want to just do is kind of look at how many lines it takes to do this. Okay, quite a bit, right? So it takes basically how many actual lines? 30, basically 30, roughly, actual lines of the table. Okay, and how many states does it take? Well, he's calling his states 0, 1, 2, 3x, 3y, 4x, 4y, 5, 6. Okay, and 7 and then also halt. Okay. All right. So he's got 7 different states, 8 different states, 9, a bunch. Okay. He's got a bunch of different states. Um, and what about our symbols? The underscore here is how you would type a space. Okay, since you can't really type a space. So he's got space 1, 0, 2, or sorry, I misread that. Space star X, Y, 1, 0, and I think that may be it. Yes, okay. All right, so let me run this thing, and here's 2 numbers that it's going to add. Okay, so he's using X and Y almost as like temporary symbols, and then he goes back and overwrites them with ones and zeros and stuff as appropriate. Okay, um, and we can check that in fact is the correct addition. Everything's cool, right? But as you can see, like this is starting to get unwieldy. Okay, um, in the sense that, well, yeah, we could go through it and figure out all of these steps or whatever. It's not practical to actually do this and actually get some programming done when it gets this messy. Okay, so what could we do instead? Well, the author of the book defines a language, which let me go into. Oh, of course, I don't have Bison. Okay, hold on. Um, have to install the package. Okay, got some warnings, but no. Okay. Okay, I'll do this on my laptop instead and get it working on the Pi later. So let's see, Mac, Auto, and let's go to here. Oh no, actually, wrong thing. Sorry. I need to pull up Linux. Okay, so I'm now, it's operating systemception, right? So I'm running Linux within Mac OS, and that's what's on the screen. Yeah? Okay. All right. So the book defines this language called BareBones. Okay. BareBones has, well, not a whole lot in it. And yeah, pretty much. Okay. So let's look at the README for this thing. Okay. So the language has the following stuff in it. Okay. You can have variables that are named essentially whatever you want. Okay, with some exceptions. Okay, and then here are sort of the reserved words, which is to say these are the things that are part of the language that you can't name a variable because they have they have a special meaning. Okay, so we have the following: clear, copy, decr or decrement, do, end, increment, init, not, to, and while. Okay, and the a lot of these come in groups. So, like for example, the copy and the to go together. So what you would say is, for example, copy x to y. What does that do? Takes whatever the value of x is and copies it to a new thing called y, or another variable called y. Okay. Um, and we'll look at the rest of these in a second. Okay. But what we want to kind of think about is, first off, is this language Turing complete? Okay. So what does it mean to be Turing complete again? Yes. It's computable by a Turing machine, okay, or anything that's equivalent to a Turing machine. Okay, so if we have a language like this BareBones language, and we can demonstrate in some way that each sort of primitive piece of it is a Turing machinable thing, then combining them is just going to be a, well, more complicated Turing machine, but then we have something that's Turing complete. Okay, now this language in some cases or some senses sort of looks like Python, not completely, um, but you'll notice that there's maybe a glaring omission, and perhaps you guys can spot it. What do you think might be a glaring omission here? There's no adding two things together. Okay, that seems pretty bad, right? Okay, now the thing though is, and that's maybe it'll be our first program, is we don't actually need to have a plus operator, right, to be able to add two things. I can build addition with the pieces that are there, hence why it's called bare bones, right? So, uh, yeah, so in the same way, there's no subtraction, or for that matter, multiplication or whatever, right? Would it be convenient to have those? Yes, but is it necessary? No. Okay, what else is sort of glaring and missing? This one's maybe a bit more subtle. Yes, fair. Um, the start, like, I guess maybe the convention is you just start in the start. Like, there's no states here either, right? So where do you start with a list of a code at the top, and you just keep going down? Well, what about the conditionals? Do you see if or then? No, right? Which I think we kind of, when we were talking about like the Lego set construction and all the algorithm, like how we describe an algorithm, we found that an if then or if then else kind of construction was really handy, but it's not there. Okay, which begs the question then how do you build it out of what is there? Okay. Um, there's also no for loop, and that's okay. Um, because we could again build it out of these primitive pieces. Okay. All right. So what we have, this thing that I'm going to run is a basically a simulator for this language. So it will, if we write a program in this language, then this program that I have will execute it and tell us what the, excuse me, what all the variables are when all is said and done. Okay. It's not a particularly complicated language, but it's also sort of feels like it's missing some things. Okay, so let's look at maybe a couple of examples of this. And so let me open up VS Code and let's start making some things. Okay, and in fact, let me also make a folder for programming, and we'll make a new folder for bare bones. And it's going to complain about me not having things installed. All right, so let's make a new file on this. We'll call this adder.bb. So in this language, and let me blow up the text a little bit so it's a little easier for you guys to read. Let's see, view, appearance, zoom in. Okay, all right, that should be good. All right, so let me do the following just sort of as an example. Okay, so this is maybe the first construct. So the while loop in this language is very basic in the sense that it will continue looping until some variable is equal to 0. Okay, so if I have, for example, while n not 0 do decrement n, okay, what's that going to do? Let's say that n starts out as 10. It's going to decrease 10, 9, 8, 7, 6, and so on until it hits 0, in which case the loop will finish. Okay, so what about if I forgot to put that decrement in there? It would be an endless loop, right? Because let's say n starts at 10. Well, if I don't change n during the course of the loop, then I'm just going to loop forever, okay? Which is probably not a good thing for practical purposes. Okay, so this is the simplest little program, or pretty close to the simplest little program we could write, okay? And now let me open a terminal, and let me just use, yeah, we'll use just PowerShell, that's fine. Okay. And oh, the other thing I want to do real quick is just for convenience, I'm going to move I'm going to move all of this. Oops. So I'm going to move this entire file, this folder, to the programming folder, just so I don't have to do, okay, so we'll skip that one. Okay. Okay, so let's do, and you know what, I really don't like, well, we'll just use PowerShell, that's fine. Okay, so BareBones, and I'm going to say n equals 10, and then the name of the file. Okay, so what I've done is I've told the simulator, I want you to do this, and I want to start where the variable n is equal to 10. Nothing special about the number 10, I just sort of picked that. Okay, all right, and it's going to run through and do everything, and then it'll tell me the final values of the variables, which in our case here, why does it make sense that n ended at 0? That's when the loop ends, okay, when n hits 0. And when the loop ends, I would continue to the instructions after that end line, but there are none, right? And so that's it. The end here, by the way, is ending this loop, not the whole program, okay? So, right. Okay, now that's not really all that exciting, right? Being able to count down from whatever, okay? So let's think about how we might do addition, where all we have is increment, decrement, and this loop, okay? So let's suppose that we have the numbers, just for sake of example, 5 and 3, okay? The sum of which is, of course, 8, yeah? All right, so think about for a moment, maybe sketch it out on paper or something. How could you add 5 and 3 without actually doing addition like you might have in grade school or anything? Okay, hold on. Don't spoil it yet, wizard. Okay, and the key here is what tools do we have at our disposal? Increment, which adds 1 to a thing, decrement, which takes 1 away from a thing, and this while not construction. Okay, that's it. Okay, so any brilliant ideas from the peanut gallery? Thomas.
Well, n not 0 do decrement and increment m.
Right, okay. So what should we call our two numbers? How about n and m, or x and y, right? It doesn't really matter, okay? So let's say our numbers are 5 and 3. okay? And let's just say it's n and m like that, okay? So what I could do is I could increment one number and decrement the other, right? So if I increment one number, let's say that turns into 6, this turns into 2, 7, 1, 8, 0. Yes? So what I want to do is I want to increment one and decrement the other until the one I'm decrementing hits 0. And then I know I'm finished because I've sort of run out of the second number. Okay, does that make sense? Okay, is this kind of a silly way to do addition? In some sense, I don't know. Maybe this is kind of like how you guys did, um, like, let's go back to like kindergarten, first grade kind of arithmetic. All right, how might you do this with like a 5-year-old to ask them to add 5 and 3? Huh? You give them physical objects, right? So you say, okay, here's 5 marbles and here's 3 marbles. Okay, how might they do it? They might say, okay, well, there's 5 marbles here, so I'll take 1 marble from the other pile. Okay, now this pile has 6 marbles. Okay, now it has 7 marbles. Okay, now it has 8 marbles, and my other pile is now out of marbles, so there are 8 marbles, right? Okay, is this like the most efficient or expedient kind of method of doing addition? Oh, of course not, right? But is it make sense? Yes? Okay. So um, let's change our program here. Okay, and so let me change this to m because that's what we called the second number. Decrement m, increment n, and that's it. Okay, so the only thing I need to specify then is what are my starting values? Well, what was the starting value of n? 5. And what was the starting value of m? 3. And of course, I just made those up. And sure enough, what do we get? N hits 0, or sorry, m hits 0, and n hits 8. And it would have probably been wise if I'd put these in alphabetical order. What do you guys think? No? Where's Thomas? Yeah, here. Let's actually, Thomas, would you come over here for a Snapchat photo? I want you to look really angry. Thomas, our wizard, is going to, and then you're going to meme it. Yes, and then you like put some text on there that says "You shall not pass." Yeah. So stand here, right? Look angry. I'll look angry. Okay. Yeah. Yeah. You shall not pass. Right, because that's what it is in Lord of the Rings. Okay. Okay. So Gandalf the Brown over there is yeah. All right. So does that kind of make sense? Now let's think about then why is this sort of how do we know that this is justified from a Turing machine sort of standpoint? Well, have we built Turing machines that increment and decrement? We have, right? We've we started with the one that incremented, and then last time we built the one that decremented. Okay, and could we combine those in some sort of way to be able to increment one thing and decrement another? So something that incremented one number and decremented another. Yeah. Okay, now let's think from a Turing machine standpoint, what would we probably have to do? We'd probably have to add in some labels, right? Because if I just have 2 numbers, well, how do I keep track of which number is which? Well, how do we keep track of our number if we only had one number? We put it in between 2 x's. Okay. Well, couldn't we use letters as like variable names as labels, right? So, for example, let's say that our tape had, um, let's say, started with an M, then it had the number for M, then it had, say, a second M to say that's the end of it, and then it had an N followed by the number for N, followed by the letter N. Right, and the whole thing was just one big like variable sandwich. Yeah, we could sandwich it in between 2 x's, for example. okay? We didn't necessarily have to, right? But yeah, we could combine those things and build a Turing machine that effectively implements this, okay? Now, this, or the incrementing and decrementing part, right? Um, the other question, though, we need to have is, well, how can we tell if a thing is not zero or is zero for that matter, right? How would we build a Turing machine that detects whether or not a given thing is zero or not?
States.
Okay. Well, yeah. Okay. So what states would we want to have? So let's suppose again that I have a binary number that's stored in between two x's, so I kind of know where it starts and stops. Okay. How could and I start at the right-hand side of that thing, starting on the x. Okay. How would I scan through it to detect whether or not I do or do not have a zero? Well, I'll do it one bit at a time, right? Because what is the encoding of zero? All zeros. So if I hit a 1 at any point as I'm scanning right to left, what do I know that I have? Not zero, okay? And how do I know that I can stop scanning when I hit that left-hand X, right? So this is why having the X's or M's or, some symbol to kind of delineate where does the number stop is convenient. Okay, so if I can tell whether or not something's zero or not, I can add 1 and I can subtract 1. Could we Turing machine this thing? Yeah. Would it be maybe kind of complicated and messy? Sure. But it's Turing machine doable, and therefore we're justified in using this in some way as a shorthand. Okay. Okay. So the other, what are the other pieces of language that we haven't maybe used yet? We can copy a variable to another variable. Okay, so for example, here I could do something like when I finish this loop, what is the value of n? Or sorry, m? 0. Okay, well, maybe I needed to keep track of the number that it started as for some other reason. Okay, so I could, for example, copy m to, let's just say, x. Okay, and then when I'm done, I could say copy x to m, right? So then what have I done? I've sort of made a temporary copy of the variable and then changed it back when the loop finished. Okay, maybe I need m for some other thing. I don't know. All right, so let's see what happens if I run that. Okay, well, what did I initialize x to be? So if I don't specify it, what's the assumption? That it's going to be 0. Okay, fine. And what are our final values? X, m, and n. Okay, and so I just basically copied the 3 from x back to the variable m for posterity. Okay, because again, let's suppose that I had other arithmetic that I wanted to do later. Okay, okay, does that kind of make sense? All right, so we can also clear a variable which just sets it equal to 0. Okay, makes sense. Do we really actually need that? No. How could I clear a variable, set a variable to 0 without clearing it? Right. While, exactly, right? So let's say that I have a number. How can I make sure that it equals 0 or force it to become 0? Well, I could do while that number not 0, do decrement that number. So what happens if the number starts as 0? Then you don't decrement, you don't even do the loop. And if it is, you just keep taking 1 away from it until it hits 0. Okay, now is that particularly convenient? No. So the language defines clear basically to be a shorthand of that. Okay, but if we wanted to, I don't know, maybe we could strip out what's even not necessary here and call it bare bone, right? Forget having multiple bones. It's just like a femur on the desk. That's it. Huh? It is. Yeah. You have multiple bones? This reminds me, since today's Halloween, um, I saw a picture from it must have been from Walmart or Target or somebody that had their aisles upon aisles of Halloween decorations, and it was a spider skeleton. There's just one problem. Spiders don't have skeletons. They're invertebrates, right? So it's just kind of like, well, okay. Right. I mean, it might as well have been the same thing, right? These things are invertebrate animals. They do not have skeletons. So, yeah, okay. I don't know. Maybe that is more creepy than, yeah. So, okay. So, what other, so we've seen here that even though this was kind of a weird way to write addition, isn't this a heck of a lot easier than adding two numbers Turing machine style? Okay. And just to sort of recap and make sure that it's clear, how did we add them Turing machine style? Um, well, here was an example. Okay. So here it's adding two 6-bit numbers. Okay. Let me just throw some uh, zeros in between just for. Oh, is it just me or did the noise stop? It, yeah, it stopped. Okay. But now apparently the building's ready for takeoff. So, um, yeah. Okay. So there it added the two numbers, right? And this would essentially be what we would be doing to uh, go through, or a way of doing the Turing machining uh, this BareBones program. Okay. All right. So what else do we have in BareBones? We go back to the README file. Okay. So clear, we just talking about that. Copy, we talked about that. The do is part of the while. End is sort of how you tell it when the end uh, ends. Um, and init would be I could initialize variables inside my program rather than having to pass them in the console. So for example, I could do something like init m equal to 5, init n equal to 3, and then run it this way, and then I don't have to specify it there, and it does the same thing. Okay, that's literally it. That's all you have in this language. Okay, um, so addition, as we just discussed, was something that seemed like a glaring omission. Well, could I do subtraction in some sort of way? Yeah, I decrement both, right? And then I might have to do some thinking about like, well, what happens if the numbers are negative or something? But could we, at least for the temporary purposes, just ignore the case of negatives? We could, okay. Um, and let's see, okay, so if we can do subtraction and addition, could we do multiplication? Yeah, okay, so how might you do multiplication if you don't, what is really multiplication? It's a bunch of addition, right? So if I could add two numbers, then I can multiply them by adding one to itself according to how many times the other one appears. Yeah, okay, so we can do that. Division, well, it'd be a little bit more complicated, but yes, you could theoretically do it. Okay. Um, so what's the one omission that we really haven't specified here? The conditionals, right? Now, to some extent, they're built into this while loop construction, right? Because the while loop has to decide whether or not a thing is or is not equal to zero. Okay, and then so maybe that actually kind of gives us the key here as to how to crack it. That somehow we're going to have to use the while construction in order to get an if-then kind of thing. Okay, I don't want to spoil it, so let's just maybe leave that as something to ponder for next time. Um, but if we've got all of those things, anything more complicated, like for example, multiplication, could I imagine having like a, here's your template for multiplication and plopping it in wherever you might need to do multiplication? Okay. Okay. So again, all we have to do then is establish that all of these pieces are Turing machine doable. Okay. We already know that's the case for increment and decrement, right? And the while loop, well, okay, maybe not quite yet. We've definitely talked about how we could detect whether or not you've hit zero or not for a thing, just scan through it. Okay. Um, and well, that's basically it. Okay. So this language, we haven't fully verified it yet, but this language, as simple as it is in fact Turing complete. Okay. Is it the most convenient language? Of course not. Right. So if I wanted to build something on top of this, let's call it, oh, I don't know, sack of bones, right? You got all the bones, and they're in a giant sack.
Of the spider.
Yes, the spider bones, right? Um, then what you would have to do is say, okay, like for example, Python's for loop. Could we construct it out of these pieces?
Yes.
Somehow, yes. Okay. And therefore, Python's for loop is still within the realm of things that are Turing computable. Okay. And so that language then is Turing complete because it's built on top of another language which is Turing complete. And this language is built on top of Turing machines, which are by definition Turing complete. Okay. Okay. So this begs the question, and this is kind of where we'll part. This is sort of the other topic for Wednesday. Okay. Is if Turing complete means things you can do with the Turing machine, it begs the question, is there something you can't do with a Turing machine? Okay, so if we've talked about things that are computable, right, then that sort of makes us at least question whether or not there exist things that are not computable, right? Because if there are things, if there's nothing that's not computable, then why even have the word computable in the first place, right? There's nothing else. Okay, so spoiler alert, there are things that are not computable. Okay, and we'll kind of look at what that means, or how to rephrase the question into a way that's maybe a bit more manageable. Okay, so I'll state the question in this form. Okay, given a Turing machine, okay, and so if I give you a Turing machine, what really am I giving you? I'm giving you that big table and the initial state of the tape, right? Okay, so that's a big pile of information. Or given a BareBones program, I can just hand you the BareBones program. Okay. And so here's the question I want to ask. For a given program, can you determine whether or not that program eventually halts? Okay, so if I give you one particular program, could you determine whether or not that program will eventually halt? Okay. All right, you could think it through, right? And in our case here, right, we've written programs that definitely halt, and we've built Turing machines that definitely halt. And we said without too much trouble, we could actually create one that doesn't halt, right, that just goes into an endless loop. But could we look at that as humans and say, all right, this one definitely is going to halt, and this one's not for whatever reason? Yes? Okay. Now, what about, could I write a program that if you give it another program, it can determine whether or not that program halts or not? Well, this is a little bit more of a meta question, right? So a program, right, really just processes data in some sort of way, and a program is itself just a big pile of data. So there's no reason that I can't theoretically hand one program to another and have that second program process the first one in some way. Okay, make sense? All right, so that's the question. Is there a program that if you hand it any program, and that's the key, any program, any theoretical program that could possibly exist, it can look at it and say, yep, it'll terminate, or no, it'll go into an endless loop. Okay, what do you think? You're shaking your head. You don't think it's possible. You think it is?
I think it's theoretically possible, but probably haven't found it yet.
Well, okay, there is that, right? Um, turns out it's not possible. Okay, and we'll kind of think about why on Wednesday. Okay, so what I'd like you guys to do between now and Wednesday, just ponder upon this. Why might it not be possible? Just think. Okay, um, and right. So okay, now that the building's cleared for takeoff, I guess we can quit a smidge early today. So all right, see you guys later. Take some candy for the road.